It seems like every day we hear about AI doing something incredible, right? Like stuff we never thought possible. AI writing articles, creating images, even composing music. But have you ever wondered how far that really goes? I mean, even something as complex as advanced math is being tackled by AI now.
Yeah, that's definitely true. The progress we've seen with these large language models, the LLMs, it's
Yeah.
really impressive, especially when it comes to mathematical reasoning. We're talking about systems that can actually grapple with problems that would challenge, even experienced mathematicians.
And that leads us right into what we're digging into today. It's this really fascinating research paper. It's called Brains versus Bytes, Evaluating LLM Proficiency in Olympiad Mathematics. And like the title suggests, they're basically throwing these AI systems into the deep end, making them tackle problems from the International Mathematics Olympiad, the IMO, specifically the really tough shortlist problems they have.
Exactly. The researchers who did this study, they were driven by a question I think a lot of us have. When we see these LLMs, acing math tests, are they really thinking like a mathematician would? Or are they just finding these clever little statistical shortcuts to get to the right answer? There's this worry that just looking at whether they get the answer right might not be showing us the whole picture of what they actually understand.
Okay, so for everyone listening, that's really the heart of what we're doing today. We're going to unpack this whole thing. We want to see where the limits are. Even for the most advanced LLMs, when you hit them with really challenging math problems, can they go beyond just crunching numbers? Can they do that step-by-step logical reasoning that these Olympiad problems need? And maybe even more importantly, we'll look at why this matters. Why is it important to know if they're really understanding the math, not just getting the right answer? So, how do we even start looking into this?
Well, a good place to begin is to look at how we measure how good these LLMs are at math, right? The paper points out that there have been some big leaps forward, particularly with models like OpenAI's O1 and some others that use this chain of thought training. It's like encouraging the model to show its work, to kind of explain how it's getting to the answer.
Oh, right. And that's led to some pretty impressive scores on the standard math tests, right?
Yeah.
The paper mentions GSM-8K and math, I think, and models like Quen 2.572b, it got over 90% accuracy on GSM-8K, and O1 is almost at 95% on math. That's pretty amazing, isn't it?
Yeah, those are really high numbers, and it shows how fast things are moving in this field. But as these models got better and better at those benchmarks, the researchers, they realized we need harder tests, like the graduate level courses for AI
Yeah.
to really push them. So that's where these new benchmarks come in. Olympiad Bench, Olympic Arena, Champi, Alpha Geometry, Math Odyssey, even OmniMath. They're all designed to test LLMs with like competition level problems.
So we've got these tougher tests now, but the paper makes this point that most of them, except for a few, are still mainly focused on checking if the final answer is right. How come that's still a problem when we're trying to figure out how good they are?
Well, here's the thing, and it's really important. An LLM, it could, in theory, get the right answer, the number or the formula, but do it with completely wrong logic,
Mhm.
or just by spotting a pattern without actually understanding the math behind it. It might not be such a big deal with simpler problems where the quickest way to the answer usually means you're thinking correctly. But when you get to these really complex contest problems, having the right answer on paper doesn't mean the LLM actually solved it the right way.
Okay, I get that now. It's like getting all the multiple choice answers right just by luck versus actually knowing the subject, right? So how do we move past just looking at the answer? The paper talks about this LLM as a judge idea.
Yeah, that's become a big area of research. The idea is, can we use LLMs themselves to judge how good the solutions are that other LLMs come up with? It could mean we don't have to rely so much on humans checking everything. But the problem is, judging the reasoning in complex math, it's hard, even for human experts. So getting an AI to do it consistently and fairly, that's a really tough challenge.
I can see that. I mean, different math problems can have lots of different ways to solve them, right? And even in one attempt, some mistakes are like worse than others in terms of the reasoning. So how do you train an AI to know the difference between, say, a small arithmetic error and completely misunderstanding a core concept?
Exactly. The paper mentions some researchers are trying rubric-based evaluation. You have a model solution and specific things to look for when grading. But like you said, a big issue is that lots of these hard math problems, they have multiple right answers, and those might not match up exactly with the rubric. It's a really tricky problem.
So with all these limitations in the benchmarks and how we evaluate them, how did the Brains versus Bytes researchers actually try to understand how these LLMs were thinking? What did they do to see if these AI systems were really reasoning mathematically?
This is where things get really interesting. They chose to zero in on a very specific and very difficult set of problems. The shortlist problems from the IMO, the International Mathematical Olympiad. In the math world, these problems are famous for being original, really deep, and they need this sophisticated logical reasoning to solve them.
The ammo shortlist. Wow. Yeah, that's a whole different level of difficulty. These aren't the problems you find in your high school textbook. The paper actually says these problems are designed to be new, not solvable with just standard techniques. And while you technically could solve them with high school math, they need super intricate creative thinking. So, which LLMs did they pick to put through this ultimate test?
They picked what they called frontier models, the most advanced ones available when they did their research. That included O1, O1 Mini, O3 Mini from OpenAI, then Gemini 2.0 running in its flash thinking mode, and DeepSeek R1. So these were some of the most capable LLMs out there.
Okay, the top contenders in the AI world going up against these incredibly tough IMO shortlist problems. What happened? What did they learn about how these digital brains handle that level of math?
Well, what they found initially was really surprising and maybe a little disappointing if you thought AI was about to, dominate all kinds of intellectual tasks. Out of all the solutions these LLMs generated, only a tiny, tiny percentage were actually completely right or offered any kind of useful insight into how to solve the problems, like almost none.
Wow, almost none. That's a huge difference from those high accuracy rates we saw in those easier benchmarks. It really shows the difference between just getting an answer and really showing that step-by-step mathematical understanding.
Exactly. And when they dug deeper into the wrong answers, the researchers, they started to see a pattern. The LLMs weren't just making random mistakes. They were making the same kinds of errors over and over. And those errors, they pointed to some fundamental weaknesses in how they were reasoning mathematically. They called these common fallacies in the solutions the LLMs came up with.
Common fallacies. That's interesting. It's like there are these predictable ways that these models mess up when they're dealing with this kind of complex reasoning. What were some of the main fallacies they saw?
They grouped these flawed reasoning patterns to 6 main types. The first one was proof by example. So this is where the LLM tries to prove a general math statement by just showing that it works for a few specific examples, but they don't actually give a solid logical reason why it must be true in all cases.
Ah, so like saying, well, it works for 1, 2, and 3, so it must work for all numbers. Yeah, that's a classic mistake, even for human students sometimes. What was the next one they found?
The next one was proposal without verification. This is when the LLM, it throws out a method or strategy for solving the problem, but it doesn't explain why that method is right, why it's valid, or even if it applies to this problem. They just sort of state an approach and go with it without showing why it should work.
So they suggest a way to solve it, but they don't show why that specific way makes sense. It's like a missing piece in the logic.
Exactly. The third fallacy they found is actually pretty worrying. Inventing wrong facts. This is when the LLM just makes up math theorems, definitions, or facts. Things that don't actually exist. They use these made-up things to try and support their arguments or fill in gaps in their reasoning.
That's a little alarming. You'd think an AI trained on tons of text and code would at least know the basic math facts. It makes you wonder what they actually understand and how they're accessing information.
It does raise some big questions. Okay, the fourth fallacy they found was begging the question, which is also called circular reasoning. This is where the LLM's argument, it assumes the thing it's trying to prove is already true. So it's going in a circle, not actually proving anything new.
Right, like saying something is true because it's true. You're not going anywhere with that. What about the last two fallacies? What were there?
Number 5 was solution by trial and error. This is when the LLM throws out answers that seem like they were just guessed or found by trying a few random things, without any system or explanation for why those solutions work or why other ones were wrong.
So instead of a logical step-by-step approach, it's more like randomly trying things until something seems right, but without any understanding of the math behind it.
Exactly. And the last one, number 6, was calculation mistakes. Basically, significant errors in arithmetic or algebra that completely mess up the solution. The researchers, they were specifically looking for errors that were big enough to make the whole solution wrong.
Okay, so we've got these 6 pitfalls. Proof by example, proposal without verification, inventing wrong facts, begging the question, solution by trial and error, and calculation mistakes. It really paints a picture of these LLMs struggling with the very basics of rigorous mathematical proof.
It does. To get a clear idea of how often these problems happen, the researchers then looked at the numbers. They analyzed how these LLMs did across a whole bunch of IMO shortlist problems, 455 of them, from 2009 to 2023.
And what did the numbers show? Was there any model that was clearly better at avoiding these mistakes in its reasoning?
Table 1 in their paper sums up how well they did, and it's pretty revealing. The percentage of completely correct solutions was very low across all the models they tested. DeepSeek R1 did the best, but it still only got 3.8% right. Then it was O3 Mini at 3.3%, O1 at 1.9%, and Gemini 2.0, it actually didn't get any fully correct solutions in their tests. O1 Mini didn't either.
Wow, those are really low percentages. It's such a big difference from the accuracy they got on those easier tests. It really highlights how different it is to just get the final answer right compared to actually solving these complex Olympiad problems correctly.
Exactly. And Table 2 in the paper, it takes this comparison even further. They focused on problems with a clear numerical or symbolic final answer and compared the overall accuracy in getting that answer with the percentage of solutions that were actually completely right if they got the final answer right.
Hmm.
What they found was, even when the LLMs got the answer right, the solution itself, the way they got there, was often wrong.
That's surprising. So they're somehow stumbling onto the right answer, but the math they're using to get there is messed up. It makes it seem like they might be relying on tricks or patterns in the answers themselves instead of actually understanding the math.
That's exactly what the researchers concluded. They argue that judging these models just by whether their final answer is right, it's not good enough for these tough problems. It misses the whole point of whether the solution itself is logically valid, and it doesn't account for the possibility that these models are exploiting patterns in the answers to get there.
So what about the different types of fallacies? Did they find any patterns in which ones were more common in certain models or under certain conditions?
Figure 2 in the paper breaks down how often each fallacy showed up for each model. One interesting thing is that inventing wrong facts was the most common fallacy in 4 out of the 5 models, and it was the second most common in the other one. This might be because of how they're trained, often using reinforcement learning, where they're rewarded for getting the right answer no matter how they get there.
Yeah, I guess that makes sense in a twisted way. If the main goal is just to get the right answer, the model might learn to just make up facts if it thinks that'll lead to the right output, without actually caring if those facts are true or not.
Yeah, that's a possible explanation. Another really common one was proposal without verification. The researchers, they looked specifically at how DeepSeek R1 and Gemini 2.0 were thinking, and they suggested that this fallacy might happen because the models have trouble figuring out exactly which steps and calculations they absolutely need to include to make a complete and rigorous argument. So they end up making these vague claims without backing them up with the necessary math.
So it's almost like they know they need to show their work, but they don't really get what counts as valid mathematical work, so they just throw out general statements and hope it looks like they're reasoning correctly.
That's a good way to put it. They also looked at whether the type of question affected which fallacies were more common. Whether the problem asked for a specific answer or if it was a proof-based question. Figure 3 shows that proof by example and solution by trial and error were more common when a specific answer was expected. This suggests that the models might be more likely to guess or try things out when they have a target answer to aim for.
That makes sense. If you have a specific answer format in mind, you might be tempted to try and work backwards from that or just plug in different things until you get something that looks right.
Right. On the other hand, inventing wrong facts and proposal without verification were more common in those proof-based questions where there's no specific answer given. It seems like in those cases, the models struggle to build a logical argument from the start to the finish, so they try to fill in the gaps with made-up statements or by skipping important steps in the reasoning.
And did the specific type of math, like geometry versus algebra, have any effect on which fallacies they saw more often?
Yeah, figure 4 in the paper shows some interesting stuff about that. They found that inventing wrong facts, proposal without verification, and begging the question, those were more common in geometry problems. Maybe because a lot of geometry problems depend on logical deductions and spatial reasoning, not just manipulating formulas. And solution by trial and error was more common in algebra and number theory. Maybe because those problems sometimes lend themselves to testing out specific numbers or cases. And proof by example was more often seen in algebra, combinatorics, and number theory, where the problems are often about proving something is true for a whole bunch of different values.
It's fascinating how the ways these models mess up seem to change depending on the kind of math problem they're trying to solve. It really shows they don't have this general, deep understanding of math like a human expert would.
Right, their weaknesses aren't the same across the board. They depend on the type of reasoning needed and how the problem is structured. And this led the researchers to another question, which is really important for how we might use or develop these models in the future. Can LLMs even tell if their own math work is right or wrong?
That's a good point. If these models can't accurately judge if their own solutions or even solutions from other AIs are correct, it's hard to see how they can learn and get better, or how we could use them for anything where accuracy is really important. How did the researchers test this ability to verify math solutions?
They had this clever two-part test. First, they checked if the LLMs could tell if a genuinely correct solution was valid more often than their own incorrect solutions, the ones with those fallacies we talked about. Second, they gave the LLMs two solutions to the same problem, one that was definitely right and one with logical errors, and they asked the LLMs to pick the correct one. They told the models straight up that one solution in each pair was right.
Okay, so they were basically judges comparing solutions. What happened? Could they tell the difference between good and bad mathematical reasoning?
The results, they're in Table 3, and they're not good. DeepSeek R1 and Gemini 2.0, they were both really bad at telling correct and incorrect solutions apart. Even worse, O1, O1 Mini, and O3 Mini, they were actually less likely to say a correct solution was correct compared to their own flawed solutions.
That's really worrying. It seems like they don't fundamentally understand what a valid mathematical argument is. They're almost more confident in their own mistakes than in correct reasoning.
It does suggest that. And when they had to choose the right solution out of a pair, that's Table 4, most of them did no better than random guessing. Only DeepSeek R1 and O3 Mini were a little bit better than just flipping a coin, but their accuracy was still way too low to be reliable.
So the big takeaway here is that these LLMs, they're not just bad at solving really hard math problems. They're also not very good at judging if mathematical reasoning is correct, even when it's given to them. That's a problem, especially if we were thinking of using them for automatic grading or even as helpers for complex math thinking.
Exactly. The researchers' conclusion was that these top-of-the-line LLMs, they're just not there yet. They can't consistently produce mathematically rigorous proofs for these Olympiad-level problems. They seem to rely on shortcuts and patterns, and they can't verify solutions well. So it makes you question those training methods that are all about getting the right answer no matter what.
So after this deep dive into what LLMs can do in this really tough area of math, what are the most important things for us to remember?
For anyone listening, the key thing to understand is this. While these large language models are amazing in so many areas, their ability to really understand and reason mathematically at this high level, it's still way behind humans. Just because an AI can give you the right answer, it doesn't mean it got there through sound, logical, valid math thinking. The reasoning behind the answer is super important.
And for someone like you who wants to learn quickly but also deeply, this research shows that relying only on AI for complex math understanding could be really misleading. You might be getting answers without actually getting the logic and the fundamental ideas that make those answers true.
Definitely. And that brings us to a final thought, maybe a bit of a provocative one. If even the most advanced LLMs are struggling with this core logical stuff in math, where everything's about proof and deduction, what does that say about their reasoning in other areas that might not be as structured? Areas where the rules for truth and validity aren't as clear? What kind of understanding do these systems really have, and how should we be judging them beyond just looking at if they can produce human-like outputs? It gives us a lot to think about when it comes to artificial intelligence and how important it is to keep evaluating them critically and rigorously.